Hello and thank you for listening. My name is Mike Kachasik, and my local research project involved the evaluation of the UPS crossover temperature technique for forecasting fog for two sites on the high plains. So forecasting the onset of fog provides challenges for meteorologists in all implications of fog forecasting, but especially for aviation forecasting because of the inherent need of accurate fog forecasting that is needed by the aviation community for their safety. So to try to rectify the problem of accurate fog forecasting, aviation meteorologists at the United Parcel Service, or UPS, developed a technique to forecast fog for terminal aerodrome forecasts, or TAFs, for their specific sites. So the purpose of this study is to evaluate how the crossover temperature technique, as developed by the UPS, performs for two sites in the Goodland County warning area here in the High Plains. The crossover temperature technique was developed to try to represent the vertical profile above a site where sounding data does not exist, due to surface saturation not always leading to fog development. When the temperature equals the dew point temperature and saturation occurs, not always does fog occur. So something must be going on in the vertical profile above the site, and the crossover temperature tries to capture the vertical profile above this site. So the crossover temperature uses the Fahrenheit scale for temperature and is defined as the minimum dew point temperature that is observed during the warmest daytime hours. So whenever the warmest temperature occurs during the day, whatever the dew point is at that given moment is the crossover temperature. So during the overnight hours, if the temperature T is equal to Tx, the UPS method requires 1 to 3 miles of visibility to be forecasted for that given site. And also during the overnight hours, if T is equal to the crossover temperature Tx minus 3, then the UPS method requires a half-mile visibility of fog to be forecasted for that given location. So ASOS data from the last 15 years of available data were used for HLC, Hill City, and GLD, Goodland, to evaluate the crossover temperature technique. So two tests were conducted for each site using the crossover temperature technique for this study. The first test involved the evaluation of the crossover temperature technique for visibility using all days, and then a second test for radiational cooling days. In the second experiment, the altering of the crossover temperature was done by adding positive values back to the crossover temperature, and then considering only radiational cooling events for forecasting both ceiling height and visibility at the IFR level. So observational and forecast statistics were computed, including hits, false alarms, misses, correct negatives, probability of detection, POD, and then false alarm ratio, FAR. The crossover temperature was computed from 15Z to 3Z, and the minimum temperature was computed from 3Z to 15Z that was able to verify the crossover temperature. Just as a formality, days with missing data were excluded from the computations, and then radiational cooling days were determined based on three of the following characteristics. One, if the wind speed was less than 10 miles per hour for more than 5 hours overnight. Two, if the ceiling height was greater than 12,000 feet for more than 7 hours overnight. And then three, if the difference between the maximum and minimum temperature for a given day was greater than 20 degrees Fahrenheit. If all three of these conditions were met, then the day was considered a good radiational cooling day. So the first result here is for the T equals Tx method for forecasting 1 to 3 miles of visibility for a site. Goodland is in blue for both charts, and Hill City is in red. The chart on the left is for all days, and the chart on the right is for just considering radiational cooling days. For both charts, the hits occurred less often than the false alarms, and the correct negatives occurred more often than any of the statistics computed. These charts show the Tx minus 3 method now for forecasting 1/2 mile visibility for a given site for the UPS method. Goodland is in green and Hill City is in purple for both charts, where all days is on the left and radiational cooling days is on the right. For both instances here, the hits occur less often than the false alarms, and the correct negatives again occur more often than the other statistics for both all days and radiational days for both sites. The probability of detection and the false alarm ratio were computed for all days on the left and radiational cooling days on the right. For both the TX and TX minus 3 methods, for Goodland and Hill City. As you can see in both charts, the probability of detection occurs less often, or is a lot lower of a value than the false alarm ratio for its direct counterpart, the same color. False alarms are greater than the hit statistics for both Goodland and Hill City, as well as for both the TX and TX-3 crossover temperature methods. The false alarm ratio is greater than the probability of detection for both sites in both crossover temperature forecast methods for both all days and radiational cooling days considered. So based on these statistics, the crossover technique alone does not appear to be a good visibility indicator for either Goodland or Hill City. The second experiment of this study tried to improve statistics for the crossover temperature technique by considering only radiational cooling days, along with adding a positive adjustment back to the crossover temperature. Now, a positive adjustment is used in this instance because the negative adjustment in the previous test showed worse results than adding no crossover temperature adjustment. So we will see if a positive adjustment will make any difference in statistical values. So positive adjustments were in increments of 5 degrees and were computed from 5 to 30 degrees Fahrenheit, and they were added back to the crossover temperature to determine if observations could aid in both visibility and ceiling height forecasts. So for Goodland and for IFR visibilities and below, the chart on the left shows the hits, false alarms, misses, and correct negative statistics, and on the right shows the probability of detection and false alarm ratio statistics for the crossover temperature adjustments from 0 to 30 degrees in increments of 5 degrees. So on the left, the hits are in blue and the false alarms are in red, and you can see that the false alarms occur much more often than do the hits. And then on the right, the probability of detection increases up to 15 degrees of a temperature adjustment, and then slowly increases to about 100% at 25 and 30 degrees. But the false alarm ratio is at 0.9 and above for all crossover temperature adjustments, which kind of offsets the value of the high probability of detection found here. For IFR ceiling heights and below for Goodland, the same statistics are shown here. On the left, the hits are in blue and the false alarms are in red. And again, you can see the false alarms occur much more often than do the hits. On the right, the probability of detection increases up to 100% at 15 degree crossover temperature adjustment. But again, the false alarm ratio is at 0.9 or above for all adjustments, which is fairly high. Now for Hill City, for IFR visibilities and below, the hits in blue, again, are much less than the false alarms that occur. The probability of detection slowly increases to a little bit sooner of an adjustment at 10 degrees, but the false alarm ratio, again, is very high at 0.9 and above for all adjustments. For the IFR ceiling heights and below for Hill City, the hits on the left occur less than the false alarms, and the probability of detection increases to 100% at 15 degrees of a crossover temperature adjustment, and the false alarm ratio is pesky again, lingering at 0.9 and above for all crossover temperature adjustments. Similar results occurred for both visibility and ceiling heights, as well as between the two sites of Goodland and Hill City. The probability of detection increases with increased crossover temperature adjustment, but the false alarm ratio remained fairly high and unchanged with the increasing adjustment for the ceiling height and visibility and for both ASOS sites. So even though the probability of detection statistic was very high, the false alarm ratio was also very high, which offsets the value of the high probability of detection statistic. So even with the added positive adjustments to the radiational cooling components, the crossover temperature technique does not appear to aid in forecasting either ceiling height or visibility with the positive adjustments for neither Goodland nor Hill City. Because the crossover temperature technique does not appear to perform well for Goodland and Hill City, a third test examined wind direction combined with wind speed for radiational cases and all cases to determine if the winds can indicate fog formation. So this does not use the crossover temperature technique at all now, but rather just blindly follows climatology for the wind direction and wind speed to help see if fog can be forecasted based off of those two values. So the wind speed used was 10 miles per hour to stay consistent with the radiational cooling check. So what I do is consider all cases for the radiational cooling days for below 10 miles per hour and including 10, and then just above 10 miles per hour. I considered 8 directions for Goodland and Hill City to determine which direction occurred most often in the 15 years of available data used for this study. I considered it in increments of 90 degrees and then rotated the degrees in increments of 45 degrees in directions of north, northeast, east, southeast, south, southwest, west, and northwest in the degree increments shown to the right. So fog most often occurred for both sites when the north direction occurred. If you use the wind rose in AVN FPS, you'll also see that the southeast direction occurs fairly often. But in the data that I had used, the north direction occurred slightly more often than the southeast, so in the computations to follow and the results shown, only the north direction is considered with the wind speeds. Using north winds only and wind speeds below 10 miles per hour for all days on the left and radiational cooling days on the right for both sites, we can see that the hits and the false alarms are a lot closer in this instance compared to the crossover temperature used before. So the hits are more competitive with false alarms, but the false alarms still edge out the hits as far as occurrence goes for both of these charts. For the probability of detection in the false alarm ratio for both sites for all days and radiational days, the probability of detection actually occurs more often than the false alarm ratio does, which is good. Where the probability of detection is around 0.8, 0.9, and the false alarm ratio is above 0.5, which is still slightly higher than we would probably like for the false alarm ratio, but it's encouraging to see that the probability of detection is higher than the false alarm ratio. And now using north winds and wind speeds above 10 miles per hour, there's all days on the left and radiational days on the right for both sites. The hits are still slightly below the false alarms to occur, and the correct negatives occur the most often compared to the other statistics. And for the probability of detection and false alarm ratio statistics for both sites and all days and radiational days, the probability of detection is higher than the false alarm ratio again, which is encouraging, but the false alarm ratio being at 0.5 and above and even approaching 0.6 for Goodland in the radiational cooling days column is still a little bit higher than we would like. Considering combinations of all days, radiational cooling days, winds below and above 10 miles per hour, the statistics were similar between the false alarms, the hits, the probability of detection, and the false alarm ratio. The false alarm ratio is diminished when not using the crossover temperature technique and using just the wind direction and speed compared to using the crossover temperature technique in tests 1 and 2. Slightly better probability of detections were found for radiational cooling days compared to using all days, but there was also a slightly higher false alarm ratio when using radiational cooling days compared to all days. So there's a little bit of a trade-off there in which data set is used. The exact UPS crossover temperature technique does not work for Goodland or Hill City. Altering the crossover temperature for just radiational cooling days does not really improve statistical measures either. But using just wind speed and direction without the crossover temperature for forecasting fog, based on just blind climatology, lowered the false alarm ratio compared to crossover temperature techniques, but not low enough to meet the IFR GIPR gold standard of 38% for 2013, whereas the false alarm ratio found was between 0.5 and 0.6. It is possible that advection fog cases are more common for Goodland and Hill City, so further work could examine good advection days compared to good radiational cooling days for use in this study. The methodology behind the development of the crossover temperature technique was to represent the upper air profile above a site, as well as it being unchanged from day to night. But because upper air profiles rarely stay unchanged for that given time period, Sounding profiles could be useful to aid in understanding fog development in relation to surface observations for use in this technique. So another site along the high plains with upper air data would be useful for future work. Perhaps an upstream approach could be used, incorporating moisture advection from sites upwind of Goodland and Hill City. Dew-point data would be needed, combined with wind direction and speed, and this might be a better forecast indicator of fog development. However, a potential problem would be archived data availability from AWOS sites because that archived data is limited, serving as a potential problem getting available needed data. I want to thank Jeremy Martin for many helpful discussions and help with data acquisition for this study. And I also want to thank Chris Schaefer for help developing the radiational cooling technique that was used in this study as well. I want to thank you for listening to this presentation, and if you have any questions, you can direct it to me, Mike Kachasik, in person, or at michael.kachasik@noaa.gov. Thanks again.